The frontier of artificial intelligence isn't just about bigger models. It's about fundamentally rethinking how machines learn. For years, we've relied on a single dominant paradigm, gradient-based optimization. Backpropagation, Adam, stochastic gradient descent. These are the engines that trained everything from image classifiers to large language models. But what if we're hitting a wall? What if the real bottleneck isn't compute or data, but the way we're teaching AI to learn? Let's talk about a quiet revolution happening under the radar: neural operator learning. This isn't just another neural network architecture. It's a paradigm shift in how we model complex physical systems, solve differential equations, and simulate phenomena that have historically required weeks of supercomputing. At its core, neural operators are designed to learn mappings between entire functions, not just individual data points. Traditional models treat inputs and outputs as discrete vectors. A neural operator treats them as continuous functions. That means instead of predicting the temperature at 100 specific grid points, it learns to predict the entire temperature field across a domain, no matter how many points you ask for. This is a game changer for scientific computing. Consider fluid dynamics. Simulating airflow over a wing using traditional methods like finite element analysis can take hours, even on powerful GPUs. Each simulation requires discretizing space, solving massive systems of equations, and iterating until convergence. But with a neural operator trained on thousands of such simulations, you can approximate the solution in milliseconds, without ever solving a single equation again. How? Because the neural operator learns the underlying operator, the mathematical rule that maps a set of boundary conditions or initial states to a full solution. It's not memorizing data. It's learning the physics. And here's where it gets deep. Neural operators are built on functional analysis. They operate in infinite dimensional spaces. The model doesn't just learn a function, it learns a mapping between function spaces. This is mathematically rigorous. Think of it as a neural network that doesn't just process numbers, but processes entire functions. One of the most powerful frameworks here is the Fourier Neural Operator, FNO. Developed by researchers at MIT and NYU, FNO uses Fourier transforms to efficiently capture long-range dependencies across spatial domains. Instead of processing each point in a grid individually, like a convolutional neural network, FNO transforms the input into the frequency domain, applies learned filters, and transforms back. This is critical. In physical systems, interactions aren't local. A pressure change at one end of a pipe affects the entire system. FNO captures these global interactions with a fraction of the parameters required by traditional CNNs or transformers. But FNO isn't perfect. It struggles with sharp discontinuities, like shock waves in supersonic flow, because Fourier representations assume smoothness. That's why newer variants like the Graph Neural Operator, GNO, and DeepONet emerged. DeepONet, for example, separates the solution into two branches. One encodes the input function, like a boundary condition, and another encodes the solution operator. This modular design makes it more interpretable and better at handling non-smooth phenomena. And here's the real kicker: neural operators are generalizable. Train a model on a set of fluid flows with different Reynolds numbers, boundary conditions, or geometries, and it can generalize to entirely new configurations it's never seen before. That's not just extrapolation. That's true transfer learning across physical systems. This isn't just theoretical. Companies like NVIDIA are already integrating neural operators into their simulation stacks. The NVIDIA Modulus framework allows engineers to train physics-informed neural operators that can simulate everything from heat transfer in microchips to seismic wave propagation in oil reservoirs, without writing a single line of finite difference code. But we're not done. The next frontier: physics-informed neural operators. These models don't just learn from data, they embed physical laws directly into their loss functions. The model is trained not just to match observations, but to satisfy conservation laws, like mass, momentum, and energy. This means even with limited data, the model produces physically consistent results. It's like giving the AI a built-in understanding of how the universe works. And when combined with active learning, you can reduce data requirements dramatically. The model identifies the most informative simulations to run next, optimizing the training process itself. So where does this leave us? We're moving beyond black box prediction. We're building AI that understands the structure of physical reality. Neural operators are not just faster. They're more accurate, more generalizable, and more trustworthy in high-stakes applications like climate modeling, aerospace engineering, and drug discovery. The old way of simulating the world was to break it into tiny pieces and solve equations, step by step. The new way: train a neural operator once and instantly simulate any scenario in a domain it's seen before, across scales, geometries, and conditions. This isn't the future. It's happening now. And it's redefining what it means to simulate reality. Because in the end, the most powerful AI isn't just smart, it's wise. It learns not just patterns, but principles. And that's the real breakthrough.